right. Thank you for having me here. Very happy to be here. I was really worried I'm not going to make it because my flight had issues yesterday, but I made it, so I'm happy to be here. I'm going to talk about learning quantum matter. I don't remember whether this was exactly the title, but I'm sure it was something along this line. But before I start my talk, I want to first advertise our new NSF AI Institute. We just launched. October 1 was our launch day. You can find out more about our institute here at our website. The most important message for you today is that I was told that there are many young people participating in this workshop, and we are recruiting. We are recruiting postdocs. This QR code will take you right to the application form if you're interested. Our AI Institute, so there are some 20-something AI institutes across the country, NSF AI institutes. There is one at MIT, which is one of the first-generation AI institutes. Our AI Institute, Artificial Intelligence Materials Institute, AIMI, AIMI is the only NSF AI Institute that is dedicated to materials research. And our mission is to advance trustworthy fundamental AI, where trustworthiness comes from trying to stay true to experimental observations and the scientific facts, and using that AI development to make advancements in discovery of new materials. So, well, Northeast, right now it is beautiful, but sure enough there will be snow. So you're not unfamiliar with seeing snow. So where is this picture from? This is a picture taken from Amundsen's expedition group. So Amundsen and his team were the first to conquer South Pole. They made it to the South Pole. And in those kind of expeditions, trailblazing, really truly trailblazing work, there is that moment of great reward where you put the flag down. But leading up to that moment is a lot of hard work and a lot of problem solving and a lot of dealing with unexpected situations that there isn't predestined, pre-existing solutions or formula. So what I want to, because I'm giving the first talk also, I want to invite you in this thinking about what AI can do for quantum materials research or quantum matter research. I want to encourage everyone and invite everyone to be resourceful in how you try to approach problems, and at the same time be principled. We're physicists. We're not trained as AI researchers, and we bring our training, our strength, the way we think to the problem. But at the same time, be curious and be mission-oriented. So what I want to avoid is using AI for the sake of using AI. What I want to accomplish ultimately is making progress in solving scientific problems. So that's my mission. I want to make advancements in science. I want to make progress in the questions that we are after. So how does our research process work? We typically start with some problem statement that might be initiated by some puzzling observations. And we want to, at the end of our research, we want to arrive at some new insight. So if you arrive at new insight, that we deem the adventure successful, so that would be the mission. So how do we go from problem statement to insight? That's the whole research process. Well, we think of something to do. We got to do something. That's the operations. We have to design operations. So that would be whether you're a theorist or whether you're a computational person or whether you're an experimentalist, you'll be choosing some tools, some approach to do something. You got to do something. What do you do when what do you gain when you do something? You don't immediately go from doing something to insight. You first get results that you generate data. And then you have to think about what that data means. So that's going from data generation to insight. So in the first part of my talk, I want to focus on these aspects. This is sort of the aspect that perhaps we have not been giving enough thoughts into. We've gotten better at producing data. We've gotten better at producing results, but we may not always know what to make all of those results. So that's the aspect that I want to focus on, because when I focus on how do you go from data to insight, that's the data-centric approach. So how do we engage with data? Scientists have always been engaging with data. When you want to go from data to insight, we call it data analysis. You have some bunch of data points. You will typically make plots. Once you have some discrete set of data points, you'll be kind of compelled to make fits, and maybe you'll be interpolating. Now, if you have some idea that you think is the correct way to think about the problem, you'll be typically doing forward modeling. That's using physics knowledge to make a spherical cow. So how do machine learning approaches engage with data? So going from data to insight will be classification or clustering. Classification is often supervised, that is classic cat versus dog. Clustering is you're grouping data into different groups, trying to discover some underlying trends. Now, going from data, instead of going from insight, if you use data to find some latent information so that you can make more data, that's called generative modeling. So although somebody like me, when I was growing up, machine learning was not something that will be discussed among the physicists, but even my training was very much centered around thinking about data. What I've been doing most of my young adulthood would be called phenomenology. And what's kind of fun about the age that we're living in is that if I tell my father, over 80, that I do phenomenology, whether I use English or Korean, he wouldn't understand what I mean. But if I say I am, doing machine learning on data, that's now something that people in general can understand. So in a way, something that we've been always doing has now gotten a broader context. So, but I've already declared that I don't want to do machine learning for the sake of doing machine learning. Something that I really don't like doing is killing fly with a sledgehammer. So if I want to bring in new tools or some hefty tools, I want to make sure that the problem actually calls for new tools. So that's looking at hard data problems that need some new tools. There are two types of hard data problems that I want to talk about. One is big data in high dimensions. So one concrete setting under which you get a big data in high dimension would be dealing with the Hilbert space, exponentially large Hilbert space of quantum many-body system. You're dealing with quantum state that lives in a very large vector space. If you have a state that is spread over, whose weight is spread over all of those available Hilbert space, that's a complex state, and that presents a hard inverse problem. Another problem that concrete example of hard data problem in large dimension would be large diffraction data. And if you have, for instance, first of all, if you are doing diffraction, you have three-dimensional reciprocal space, you have intensity distribution in that space, but you would have other control knobs such as doping, pressure, temperature, composition, and that can present a large data problem. So big data in high dimensions is a typical setting, is one setting for which hard data problems emerge. Another place where sort of a challenging data problem emerges is trying to deal with data that's been accumulated over time. So when a particular material property has been studied for a long period of time, there is that whole accumulation of human effort. Superconductivity has been studied for 100 years. So there is 100 years of humanity's effort in a large collection of papers. I can barely hold my attention for reading one paper. Maybe I can remember something for 10 papers, but there is no way I can stay awake paying attention to 30,000 papers. But there are that many papers on that topic. So how can we build on what's been studied until now in a comprehensive way and see what we can learn? That I think of as another kind of data problem. So let me start with the large dimensional Hilbert space of quantum many-body systems, complex quantum state. So let's say I have some large number of qubits. Here for concreteness, I'm showing 36 qubits. Here, these are block spheres. But you notice that all my qubits are in a state where they are all along the measurement basis, that is z basis down. This means although I have many qubits, 36 is not really many, but you can make it 3600, doesn't matter. No matter how many qubits I have, I can be in a very simple state where there is only one out of all possible states are being accessed. So that's a very simple state. Now, that's not why we would, trying to realize a state like that, such a fiduciary state is not what we would be making quantum computers for. So then what are we making quantum computers for? What do we want to do with quantum computer with many qubits? The states that we would want to study would be generally a complex state where the weights that you are actually making use of the large fraction of your entire Hilbert space. So what is being plotted here is, imagine that I have certain state and I'm looking at the probability distribution over 2 to the n bit string possibilities. Now, if I have a complex state that is generally anti-concentrated, meaning the weights are distributed, this means each of those 2 to the n possibilities have some probability, but in order to observe that, I will need to make many measurements. So complex states are like Janus. It's got two phases. One phase is that because of the spread in the weight, in other words, because of the massive superposition that you have prepared, you might be able to access some classically hard problems. You might be able to set up one state which can give you many solutions at once. So that's the positive side of this Janus. But there is another side that is this kind of complex state would necessarily make it hard to figure out what you have. That is a challenge of reading out. So this challenging to read out aspect is something that I want to try to address with AI. Complex states have large sample complexity, and it means hard inverse problem. So the question is, can you figure out what kind of state you have with finite amount of measurement? And this is something that we approached with a large group of collaborators. 3 people from my group, Haejin Kim, Iching Zhou, and Yichen Xu, are equally contributing first authors. We had a pleasure of working with my colleagues from computer science and various experimentalists and former postdoc at Cornell, who's now at Google, Yuri Lenski. The paper finally showed up. I think it was just last week, so I'm excited that I can actually give the journal reference now. You can find more about the paper in this, more about the work in this paper. But what we proposed in this work was to use what we call quantum attention network. But quantum attention network uses attention mechanism as a way of trying to learn the shape of the distribution in this large dimensional space. And attention mechanism, as some of you might know, is something that is used in the language models. But we had to we had to adjust the structure. We had to sort of invent our version of using attention mechanism for the problem. So something that I've learned over time, trying to use AI tools for quantum matter research, is that it's always, always we're trying to solve hard problems, and if you're trying to solve hard problems, giving a lot of thought into what is the structure of your data, and how does that compare to, say, structure of data some popular algorithms are designed for. Respecting the structure of data can mean make a big difference in how much value you can get out of tool. So in this case, what we focused on is the fact that when we have many measurement outcomes, these are all Z-basis measurement outcomes, we want to sample the state many times in order to study what kind of state we have, but we don't want to sample the state 2 to the n times. So we will be having sparse samples, and from sparse samples trying to understand what kind of state we have. And that requires us to learn sort of a distributional property. We want to look at multiple measurements at once instead of one measurement at a time. So if you are thinking about a transformer and sort of tokens, you don't want to treat each snapshot as a token. You want to treat a collection of snapshots as a token so that structure inside can be learned. Because each token will be handled independently, individually. Now, one can, in principle, learn structure with enough of them through the training process. But when you give a whole collection at once, you're setting up the model in a better position to be successful. Now, when we give a whole collection of snapshots, we have to remember that these snapshots are randomly taken, and there is no particular meaning in the order in which those snapshots occurred, which is very different from the language problem. So language problem is called sequence model problem, because in language, the order of words matter. But here, each of my snapshots, the order in which they occur, have no meaning. When we were discussing this problem, it took us several months. We had months and months of failing. And then we had to really sit down and try to understand, why are we failing? What are we not capturing? When we first initially used just the vanilla transformer off the shelf, it didn't work. We had many ways of failing, which is all documented in the paper. But ultimately, what we came to understand is that we really want to reflect the permutation invariance, the fact that these samples are permutationally invariant. That had to be built in, because something that we learned is that all these models, when we don't specify invariance, symmetry, it will by default assume order matters. It will by default assume the structure that we haven't specified to be invariant has meaning when it does not have meaning, and it gets hung up on that. That was the big part of what we had to solve. And then came this what we call mini-set SAB, self-attention block. This part came because we were trying to be pragmatic. So if we could work with infinite amount of data, we can make the set size very large, but making the set size, the collection size large, and trying to do self-attention among them came with resource limitations. So we needed to optimize on both fronts. We first of all needed to be able to work with finite volume of data, and we also had to work with finite infrastructure we have. And this mini-set SAB was something that we invented in order to optimize in our resource needs. So what are the problems that we solved in this approach? We looked at we carried out, let's say, quote unquote experiment, 3 different experiments. And each of these were about trying to learn to distinguish level of complexity. Distinguishing means we're doing binary classification. And why are we doing binary classification? Well, because this is a really hard thing to try to learn. So after struggling for a while and failing, we realized that if we want to be successful in this really difficult inverse problem, we need to set our goal to be something that is reachable. What is the absolute simplest thing that we can do and nevertheless declare that we've learned something? And that is distinguishing or classifying. So we set up three problems as a problem for distinguishing level of complexity. And turns out this whole notion of complexity has mathematical, like there are mathematical rigorous efforts at trying to define complexity of quantum states. And often they are discussing the so-called relative complexity, comparing two states. So this notion of relative complexity that's been developing in the sort of quantum information community sort of lends very naturally into classification or distinguishing problem. Three problems that we considered were considering volume law versus area law entanglement in a particular problem setting. This was hardcore bosons. And whether we have a topological state versus trivial state. This is by introducing error in toric code. And this problem connects very naturally to the development of decoders and learning decoding threshold. And finally, this problem was looking at the random circuits and trying to learn the depth of the circuit. Because as you do more and more, as you go deeper in the random circuit, which was sort of first introduced in the context of the quantum supremacy paper, as you go deeper, you are entangling more, scrambling more, and your state becomes more spread out. So shallow circuit, if you know the state, would have this kind of distribution with some few states having high likelihood. And deep circuit would reach hard random where your weights are really spread out. But the challenge is trying to learn whether you have a shallow state or a deep state, deep circuit state, from finite amount of measurement. So in all three experiments, our quantum attention network was successful in being able to distinguish the different level of complexity. And the way this worked was when we train with training points in the shallow limit and the deep limit, and we asked the quantum attention network to distinguish which side do you think the given data is. And we wanted to be able to do this entirely based on the measurement data alone. And the way this self-attention was suitable for this problem statement was because there is something that you want to learn through the moment of the distribution. So we have a distribution in large dimensional space. And if you want to know the shape of the distribution without being able to really fit the distribution, but you want to learn that the shape is changing, and you can do that by being able to access the moments of the distribution. We realized when we use self-attention blocks, which are a single layer of self-attention is kind of building in a second moment, and by having layers of stacked self-attention blocks, we were able to access high degree of moments, and that seemed to have really helped us learn. Building on this study of success of quantum attention network, we then moved on to develop a decoder, machine learning-based decoder, that is learning, being able to detect whether the logical information had been contaminated. And that's also a difficult inverse problem. But from machine learning perspective, what we're trying to do is we train with a bunch of data, whether with or without the logical error, and we were able to learn the decoding threshold and develop a decoder that can handle logical circuit. And this was in this recent preprint, which is going to appear in Nature Computational Sciences. Again, in this problem, we were focusing on what is our scientific problem statement and what is the structure of our data, and how do we find, design a machine learning approach that best is suitable for the problem statement and the data structure. Something that we really enjoyed doing in this process was that not only we were able to design a machine learning architecture that solved our problem, But in doing so, we gained new insight just because the model was really successful at finding the threshold that was previously unnoticed, that kind of drove us to try to understand when there is a sharp observation that kind of prompts one to think about what's underneath this sharp observation. Pursuing that curiosity, we were able to uncover statistical mechanics model that can capture air threshold in the presence of transversal logical gates. And that result has just appeared on the archive this morning. So that was, so far this was about complex quantum state in the, when you have quantum many-body system. Concretely, this was, the data would be coming from quantum simulator. And you can use quantum in many ways, but talking about quantum simulator and quantum material are, it's quite a bit different. So the first part that I just described is data problem that naturally arises when you're dealing with quantum simulator data. And now I want to switch gears and talk about data problem arising from large volumes of diffraction measurements if you have some quantum material that you want to study. And that we solve with X-ray temperature series clustering, XTEC. And this is an unsupervised machine learning approach involving the high dimensional data that is changing with some tuning knob. So this work was spearheaded by my former student Jordan, who's now a researcher at Eli Lilly, and former postdoc Krishna, who's now a researcher at Lila Sciences. This was again in collaboration with my colleague and associate director of AME, Kilian Weinberger at Computer Science. And most importantly, this was collaboration with Argonne National Lab colleagues. The first paper that announced XTEC and used it to solve problems was this PNAS, and this was really Jordan. Jordan was the one who solved all the bottleneck problem. Something that I've learned doing these projects is that there is something that physics training does, kind of unique. So my CS students, not my students, but Kilian students, computer science students might be better at knowing their algorithms. They know how to make their algorithm run more efficiently. They know how to use the GPU resources we have for their maximal capacity. Now, when we were approaching this problem that we want to learn from large volumes of X-ray data, and we had problem statement that we know the X-ray data is evolving as a function of temperature. We know something happens at some temperature that is qualitatively different. We call it phase transition, and we wanted to learn that. Once I explained what reciprocal space is to my colleague who does not know what momentum is, not to mention crystal momentum, I was able to somehow convey the notion of reciprocal space. What Kilian suggested was that we approach this with Gaussian process regression. And they had the algorithm that was working on a different problem, that was health data problem. And we tried to use that for our problem. And we just couldn't make it to train. Our data volume was so much bigger, and our distribution of data was much sparser. There were many issues that made it hard to work with. So Jordan struggled with this problem by himself. Various people tried to help, but nobody could really help in solving the problem. He started taking things apart, and he said, this is all I need to make this work. And I have the simpler model, and this actually works. And then we brought what Jordan was able to do to Kilian, and Kilian said, so you actually made it into Gaussian mixture model instead of Gaussian processes. Both Kilian and I were very impressed. Well, I was impressed because Jordan solved the problem. Kilian was impressed because Jordan solved the problem. But we were surprised and impressed. And this, like over and again, I'm seeing this kind of trend that physics PhDs can solve problems that CS PhDs cannot solve because we think about problems in a very different way. So what is this XTech, X-ray temperature clustering? Well, so this is what data looks like. This is strontium, rhodium tin, single crystal X-ray data from APS. APS is not American Physics Society, but Advanced Photon Source. This is at Argonne. And it's this is something that's been happening in the facilities around the world. All the beams have been getting brighter. All the hard drives have been getting bigger to capture more data. And the data volume has gotten so big that nobody travels with data. We know why we don't want to travel with data, but anyways, nobody travels with data. It's just too big. So what do people do? Graduate students who are working on these kind of experiments, they or their PI have to write a proposal to get a beam time. So to get a beam time is some effort because you have to plan for it. You arrive at the beam line and you don't sleep. That's what I've been told. They are just running on Red Bull for a week because they got to get their data during that week. Like I said, they don't really bring the data, and they're busy taking the data, they're not looking at the data. So they, for 1 week of not sleeping, they take data, they go home, maybe first catch up on sleep, and then you look at the data by logging into the server at the beam line. And then you would analyze it one way or another. You might be analyzing this peak or analyzing that peak. You pick a peak and make a cross section and try to fit it to some curve. You try that for a couple of the peaks that you can see and see if you can learn something useful. You may not do this for years and years, and you may not be looking at every single peak. You don't have that kind of time. If you find something useful within couple months of analyzing, that's great. But you may find after a week of analyzing that you should have taken one more data point. You should have gone down a couple more degrees lower. Then you have to repeat that cycle. So what we wanted to change was that practice, that modality. So if you take this kind of data while you are at a beam line, you can give it to XTech, and XTech will immediately sort this data into two regions in reciprocal space. Region that has to do with the points that have to do with one type of behavior, the points that have to do with another type of behavior. XTech is a clustering algorithm. It's just clustering reciprocal space depending on how the intensity is evolving as a function of temperature. XTech is not very smart. It's just a simple Gaussian mixture model. It wouldn't call it charge density wave or Bragg and diffuse. This is a name that we give once the data has been sorted and given back to us. And there is nothing black box about it. There is nothing uncontrolled about it. If this is the whole collection of intensities as a function of temperature, it looks very messy. But with your naked eye, you can kind of see that there is one group behaving this way, another group behaving this way, another group behaving this way. And what XTech does is actually give control, principled, systematic and automated way of going from what you can see with your eyes to something that is quantitative. So these are different means that's been clustered, and there is a variance that quantifies the spread of the data. And all this is doing is really clustering in high dimensional space. So if I just take two temperature points, that gives me a two-dimensional space, and you can see different clusters, and that's what is being pulled out using Gaussian mixture model. Now we were able to use XTech to make new discoveries, where we discovered Bragg glass phase in platinum intercalated erbium tritelluride. It's a system that Ian Fisher's group have intentionally disordered. So they wanted to see what happens if you take charge density wave system and you control the disorder strength. And they had lots of data. But to analyze this data to figure out what is happening that is changing as a function of doping was really challenging. What we did with XTech was to look at the zone dependencies. When you do X-ray scattering, there are many Brillouin zones that you can look at. And we look at zone dependencies, and we found the width that is independent of momentum. And from that momentum independent width, we are able to extract sort of a spread. And by extrapolating where that goes to 0, we could see beyond the resolution limit. This is the resolution limit, but by looking at being able to make this discover the trend, we were able to put a temperature as a Bragg glass transition temperature. Doing that for all of these data allowed us to map out this phase diagram. Now, not only XTech is being used for X-ray data, we are also using it for 4D or 4D STEM, which is you do transmission electron microscopy at different points on a sample. So that's two-dimensional diffraction data that you're obtaining at different points in the sample. 2 times 2 gives you 4. Now, if you change the temperature, that's additional dimension, and this is another high-dimensional setting. Judy learned about XTech from my poster presentation, and she said, well, maybe we can do that on my data too. And that actually turned out to work, and we were able to uncover that there are different regions on the sample exhibiting different transition temperature, and we were able to relate locations of different transition temperature to the stacking faults in the system. That's, you can find more details in this paper. Now, XTech is going to be integrated into CHESS and APS, where so that the users will not be going through this. Poor students who've not been sleeping will not be coming back to their data only weeks after, but they can take data, go hit a button, go get their coffee, come back, and get the result. So this is the data acquisition software, which has now XTech integrated into it. And now we're making a version of XTech where what's been so far manually selected, the number of clusters, will be learned from the data. So these are sort of the efforts of learning from large dimensional evolving data, for instance, in X-ray diffraction. Now in my final 10 minutes? Do I have 10 minutes? How much time do I have? 10 minutes? Okay. In my remaining 10 minutes, I want to talk about another paper that just showed up on the archive, where we're looking at accumulated data. Here, in my most ambitious moment, I think of this effort as really trying to build on 100 years effort of research community. And that's not an exaggeration, because we're really building on people's effort. What do we want to do? We want to predict material properties. We want to be able to predict material properties, and we want to do so by building on observations, empirical knowledge. We were not first to want to be able to predict material properties, and actually somebody who was extremely successful in learning from empirical knowledge, understanding some hidden trend, was Mendeleev. So Mendeleev came up with the periodic table in 1869. This was before quantum mechanics was understood. Without knowing the structure of atoms, he was able to hypothesize this kind of structure in all the materials, all the elements, based on what was known about elemental materials. We know periodic table works. We know periodic table is extremely powerful in allowing us to understand what happens to elemental materials. But can we go beyond elemental materials? Because Mendeleev already did conquer the elemental materials. So how do we predict material properties? If we could go from first principles all the way to properties, that would be really nice, but oftentimes that's not an option. There are many properties that we measure that are important. We don't know how to go through first principles. So what actually guides experimentalists in the lab are not my calculations, although they may say that my calculations are helpful, to be nice to me. But what really guides them are often their experiences. Their experiences that, they do their experiment and they are thinking about what they're observing. So the question is, can we learn from human experiences? So this paper that we just posted last week, we made an attempt at trying to learn to predict superconductivity by feeding data from the curated database of properties, the curated database of chemical formula, structure, and transition temperature. This was effort of a large team, and it was really fruitful collaboration between Jacob and his student Natalie and my group members. Omri is actually here. He can tell you more details. So earlier, there have been efforts since the Japanese colleagues have established this curated database of all superconductors or at least very large fraction of superconductors in the form of what's called SuperCon database. SuperCon database covers various families of superconductors, and it reports TC. But it was based on experimental observations. All these papers, 30,000 papers that I mentioned, the information was gathered from these papers. It was a huge undertaking. It was before the days of large language models. But without structural information, what you can do with that data was kind of limited. A couple years ago, there was an effort to associate structure to every entry or a large fraction of entries in the SuperCon database that is 3DSC. And the data that we looked at are from 3DSC, and specifically we focused on the structural information that were based on measurements as reported in ICSD. So what is the challenge here? Now when I say, here this is lithium iron arsenic, when I say LIFEAS to another human being, another researcher, that word, LIFEAS, this just, a couple of letters, convey a huge amount of information. You know what lithium is, you know what iron is, you know what arsenic is, you would know maybe the structure, you would know various things that are known about each element and the nearby materials. How do we convey this information, and how do we convey what is meaningful to machine? And that's figuring out features. So what we started with was trying to deliver meaningful features, meaningful yet accessible features to model, and we invented what we call graph-lit histograms. This is a way of incorporating elemental information together with structural information in an organic way. It's systematic. We go from first order, second order, third order, and you can expand as needed. We found actually second order to be most useful. In second order features, what you're getting is different elements, features of the elements. These are sort of chemical features that are known for every element on the periodic table. And the structural information that has to do with, for instance, the length of the bond. And when you take structure and chemical information together, you start to understand how the two atoms that are nearby are similar or different. And that starts to access information about the bonding. So this is the graph-lit histogram is something that we invented as a way of featurizing this information. That led us to the next challenge. It's nice to be able to specify different properties associated with these different combinations. For instance, here are many 1, 2, 3, 4, 5, 6 different two-atom combinations. So that gives us a histogram. But how do I pass the histogram information to some machine learning algorithm? The machine learning algorithm that we used with great success that is interpretable was Gaussian process regression, and that required coming up with a good kernel. What are these features doing? These features are a standardized way of capturing information. For instance, it's been well known in cuprate community that the so-called apical oxygen distance is correlated with TC, but apical oxygen distance by definition is only applicable to cuprate. But when we give the second order feature that includes interatomic distances, it can cover all the cuprate materials, and also it can cover other kind of materials. So this kind of our systematic approach can capture what is known in different families, but it is more generalizable. And we also incorporated symmetry features. So we take our features that we have designed, and we feed it to two kinds of models. One is neural network, and the other is interpretable Gaussian process. And we figured out how to use the histogram information using Earth mover distance kernel. EMD is a way of comparing distributions, and here you can see two materials that are similar have small EMD, that is, they are close by, and two materials that are very different have large EMD, and EMD becomes a sort of automatable way of capturing differences or similarity between materials. So this is our result. With the neural network, we get R2 score of 0.935. This is better than what other groups have accomplished before. But most importantly, when we use GP, which gives us uncertainty, we can assign uncertainty to our prediction. So this is comparing predicted TC from our model to true TC. This is transition temperature. And you can see that when we are undershooting, that is, we're predicting transition temperatures to be much lower than a true transition temperature, which we also tend to undershoot instead of overshooting, which is kind of nice to know. When we are largely undershooting, the uncertainties is so large. What this means is that these are all the material for which the true TC was known. But when we give the material for which the TC is not known because it has not been tested, we'll still know the uncertainty, and the uncertainty will help us decide how seriously should we take the prediction. Our features are clearly showing the important significance, especially the second order features that we introduced produce a large boost. And most surprising thing that we found after all the work was that at the end of the day, we can actually compress the feature space from 32 features that we came up with down to just 4. So just 4 properties actually give us most of the predictive power, which was really surprising. Those 4 properties that ended up with the most predictive power were electron affinity difference, atomic weight mean, column mean, and interatomic distances. Interatomic distances are about the structural, the size of the bond length. So it's not surprising that it matters. None of these are surprising that it matters. What is surprising is that just out of these 4, you can actually get 92% accuracy in predicting TC. What was previously really not much attention was given was the electron affinity difference. Electron affinity is something that can be measured. It's similar to Pauling negativity. It's about how likely are you going to pull electron. It's something that can be measured, but it's harder to think about, and theoretically, Pauling negativity is more appealing. That's what most chemists have focused. But we found electron affinity difference to be very predictive. What we want to do with all this is using our classifier. We are currently working on feeding all the crystals, inorganic crystals that are known to form in ICSD to our classifier, featureize them all and put it into our classifier. And then we will start testing the materials that are predicted to be superconducting that has not been tested before for superconductivity. Now, why would this work? Well, I cannot guarantee it will work, but there is a precedence. Iron-based superconductors were known materials. They were materials that are known to exist. Just nobody took the effort of making high-quality crystals of these iron-based materials and actually cooling them down to see whether it superconducts. So there are many more materials that are known to form than those that have been tested for superconductivity, because only those are near what's known. Once something is discovered, people study materials in its vicinity. So what we are embarking on is this adventure of trying to study all of the materials that are known to form and trying to find new superconductor from that approach. So now I'm out of time. I don't think I have time to go over the other parts of like how we automate, but there are this other aspects of research process. How do you go from problem statement to choosing what operation to undertake and actually carrying out the operations? We've been also thinking about working on how to automate some of those that are very algorithmic and therefore boring. And we're actually pushing how far can AI help and what kind of assistance can they give. So this is a paper where we explored using LLM to do Hartree-Fock calculations. And we have more recently, I think I don't have, oh, no, that's, no, I think yeah, okay. So, because I'm out of time, let me just try to get to the end. So we found that LLM, this is already old. This is GPT-4. GPT-4 could do a large part of the whole broken down version of doing Hartree-Fock calculation, that is arriving at a self-consistency equation. And we also found that you can actually use these models to generate code. That is, by giving the self-consistency equation, we have models generate code that will solve the self-consistency equation. We've developed ways to check whether those codes are operating properly. And all this is, it kind of paints the picture that there is a lot that can be done with AI. And it is now important for us to know, and especially younger generation more so, to know what is hard for AI, what is your job, what can you do, how can you stay competitive. Turned out physics is still very hard compared to math. So that's good, you know. Liang is happy. But they're already getting pretty good at it. So in this paper that also just posted recently, we've explored coming up with hard problems, benchmarks, hard problems that are hard for the large language models. And in this paper, this benchmark covers 50 different problems on various condensed matter theory questions. These are questions on various numerical framework, also statistical mechanics, and just conceptual problems. And I cannot solve many of these problems either. I'm not an expert in many of these tools. I'm not an expert in ED. I'm not an expert in PEPs, so I cannot solve those problems. However, that didn't depress me exactly, because these models that can solve some of these problems, and these models that can solve international math Olympiad problems that I cannot solve, international something else Olympiad problems that I cannot solve, are still exhibiting major shortcomings. So I want to end the talk on that note, because it kind of comes back to where I started with. The major shortcomings that we were able to put our finger on have to do with, can you synthesize information? Can you think with information that are presented in different formats? Geometry, arithmetics, algebra, and concepts like symmetry. So the reason why physics is difficult compared to mathematics, I think, is ultimately that physics involves measurement. Because physics involves measurement, we are used to thinking about visualization. We think a lot about geometry and visual like image form of information, but image in a different way. We look at image in a quantitative way. And we try to reason with visual information. We reason with mathematics and language and concepts. So if you are a narrow person, just doing, doing, and not thinking about what you're doing, not thinking about how what you're doing is related to what other people have studied, you might be doing what's going to be replaced by AI. I think the capabilities that these models, so we were able to come up with 50 problems that most models scored very low. The best model was GPT-5, under 30% success rate. But the lesson from this is that the way we think as physicists is still very much a challenging frontier, because we are used to, we sort of think and reason with physical world and experiences, using many different forms of sensory tools, especially visual information in a quantitative way, and these things are still very much far from what these models can do. It encourages you all, us all, to do more of thinking, I think. So with that, let me just finish. I talked about many different things, and it might have been, probably went too fast, and it's possibly too broad, let's say. If you found the topics to be too scattered, don't complain to me, you should complain to Liang, because I asked him, what would you like me to talk about? I have these options, and he said he wants to hear them all. So it's his fault if you are overwhelmed. But I want to end with the note of coming back to like what I put out at the beginning. In a way, the fact that you are here means you are interested in partaking in trailblazing. So when you're trailblazing, it's uncomfortable because there isn't a road ahead of you. It's not a smooth ride. It can be bumpy. You have to be prepared for it to be bumpy. And it can be hard. You can run into obstacles that you weren't anticipating. But the hope is that at the end of the trailblazing, there might be the moment where you put the flag down. If you keep your eyes on your mission and your goal. Thank you for your attention.
Any questions? Back.
So maybe I missed the point. Is it possible to reframe the quantum attention neural network?
This is for the recording, sorry.
I'm
just gonna have
into a graph neural network model, which also bases like the permutation invariance, or are they just completely two different stories?
Sorry, repeat the question.
So I was just wondering if it's possible to reframe the quantum attention neural network into a graph neural network model, which also bases permutation invariance.
I see.
Or are they just completely different?
Okay. So I think so there's a similar, let's say, philosophically it's the same, there's something shared between graph neural network and quantum attention network, in the sense that both were architectures invented and designed to respect the symmetry constraints in your physical problem. Now, graph neural network deals with equivariance, right? The fact that your molecule, whether it's this way or that way, by focusing on connectivity of a graph, it is not making this to be different from this, which adds efficiency. Similarly, by building in permutation invariance, we didn't leave it for the model to discover that the data has that permutation invariance structure and put that energy somewhere else. So the motivation and the logic is similar, but the physical property that we try to preserve are somewhat different. So in our case, it's not about connectivity of graph. It is about that we're trying to learn distribution, but we don't want the data to be treated as a sequence. We wanted the data to be treated as a set. And that was the difference. But I think the motivation is very similar. And I think this is kind of a recurring pattern. If you want to solve a problem, sort of a scientific problem that came out of a scientific system, we first have to think about what is the structure of your data. And what I found to be generally not very productive route is just taking the latest model and hoping that will work. There's no free lunch, and there's no luck for no reason. If you're lucky, there is a good reason. Yeah.
Okay, other questions? Maybe one question for each topic.
Yeah.
The superconductivity prediction of TC, have that been verified by any experiment, like new material wasn't measured before?
That's what we are trying to do now. Yeah. So what we did so far in the paper was all the data that was used for training and testing were from 3DSC. And 3DSC has materials that are superconducting, and about 2.7 to 1 ratio. 2.7 have finite TC, and 1 are the materials that were tested and did not superconduct down to the lowest temperature that was taken. But 3DSC covers subset of materials in ICSD. So ICSD has all the inorganic crystals that have ever been synthesized with known structure. So I don't know, but I don't think he's here, but yesterday I heard that our postdoc in our group have featurized all of ICSD. And some of this is kind of challenging because ICSDs measure structure and there are redundancies, meaning different groups reported different structure. So there are multiple CIF files associated with one chemical formula. And using EMD, we came up with a strategy to decide when those CIF files are too different for us to pick one versus when they are similar enough that we can go with one structure. And so this kind of pre-processing is something that we had to figure out. And then we have to build all these graphlets. But this was all done, I think, as of yesterday. So I think this week we're going to run them through our classifier. And because GP classifier gives uncertainty, we will first target the materials that are predicted to be a superconductor with low uncertainty, because the testing so far shows when the uncertainty is low, they also tend to be more accurate, which makes sense. And once we have those candidates, Leslie is waiting to synthesize them.
Last question.
Yeah, very
Different
broad
topic,
one.
right?
It's a broad one, covers all topics. So I guess I'm curious to get your perspective on what you think are the grand challenges, like in AI application to learning quantum matter or key frontier questions. I mean, you gave us a nice, diverse set of topics here. So I guess what do you see as the new frontier?
Well, it's something that I haven't covered. I covered what I solved, right? So what I haven't covered. I think generally when there is a reliable data, often you can formulate a data-centric problem statement and try to attack that problem. When you don't have reliable data, then it's kind of challenging to approach from AI. So more specifically, say many-body wave functions. We know how to do variational, and we think about different frameworks, and now there are a lot of efforts in neural quantum states. There were really exciting progress made in neural quantum states, and I think maybe we'll hear about them in the conference. But still, for instance, like lattice problems are, there's much more progress in continuum problems. And these kind of boil down to, I think maybe, I'm sorry, I'm rambling, didn't get much sleep last night. I think it kind of comes down to the fact that AI models are ultimately classical, and quantum many-body problems have structure that have to do with quantum nature, and how much can we capture the essential quantum ingredients in some AI modeling can make a big difference in whether we can make progress on hard problems. For instance, frustrated spin models. Do we know what is the ground state of J1, J2 model? This spin liquid, that spin liquid, or what? There are no reliable training data, so you cannot train. Maybe if you figure out a good way to capture the possible, like a good neighborhood of potential wave function, maybe that will be a good way. But AI, like neural network-based models are generally, they're implementing the symmetry, SU2 symmetry. That's hard. Fermions need to have fermionic statistics. That's also hard. Now, there are some progress, like, you can use determinants in a productive way, a creative way. Maybe you can use Faffian in a creative way. But we know statistics is really important. So I think in order to have a chance at success, we need to make sure we capture what we know to be important, for sure. It's not always easy to capture them. I think that's where the challenge lies.
Okay, great. So let's thank Eun-Ah again.